In this video, we will study parallel electric circuits. We can define two components to be connected in parallel if the voltage across those two components is the same. For example, if I have two resistors that are connected in this way, and now you can see that the voltage across both of these resistors would be the same. For instance, we can say that the source voltage is equal to Vs, and this is just a number. It can be 3 volts, 5 volts, 10 volts, whatever it is. It's the voltage produced by the battery. And as we discussed before, the voltage drop on any copper wire is 0 volts. So this means I have the voltage Vs over here, and I have the voltage Vs over here. Similarly, the voltage on the negative terminal of the battery is 0 volts. So I have 0 volts all around this copper wire. So this means I have 0 volts here and I have 0 volts here. So you see the voltage across both of these resistors, R1 and R2, they both have the same voltage drop. So if voltage is same, then the components are said to be connected in parallel. So these two resistors are connected in parallel. Now we want to solve this circuit, and by this we mean we want to find the current flow in each resistor, and the voltage we already know that it will be the same. So to find the remaining quantities, one of them is how much is the current that will be supplied by the voltage source. So we want to find that current. Secondly, we want to find how much current will be flowing in resistor R1. So we will call it I1, and how much current will be flowing in resistor R2. So if we know all these values, then we can find how much power will be dissipated in each resistor and so on. So that's what we mean when we say we want to solve this circuit. To be able to solve this circuit, we will create an equivalent circuit for this circuit. And by that we mean that we want to draw the circuit in this way, where R equivalent or R total represents the parallel combination of R1 and R2. So we want to find R total, and once we know R total, then we will be able to find the current I that the supply will be providing. So previously we saw that two resistors connected in series for a series circuit, we found that the total resistance was equal to the sum of the resistors that were connected in series. So that was for the series circuit. Now this parallel circuit is slightly different. Looking at the figure over here, we can say that the total current I that will be produced by the source, it will be equal to the current I1 plus I2. And you can see that if you imagine that current is like water flow, so the amount of current that is coming from the supply will be divided between the two resistors, and depending on the resistors values, in one path we will get more current, in the other path we will get less current. So I1 and I2 may be different, but we can very clearly see that their sum will be equal to the total current that was provided by the supply. So this equation, I equals to I1 plus I2, later on we will see it has a name, but for now we can agree that this equation is correct. So if I want to find the resistance, the total resistance using this equation, we can see that one way would be to use Ohm's law. And Ohm's law is that V equals to IR, so this means I is equal to V divided by R. So we will apply this law for each current value over here. So now I is the current that is provided by the supply. And the same current actually flows in the total resistance, all right? So I want you to understand that this current I and this current I. These two are equal because this is an equivalent circuit. The circuit on the right is an equivalent circuit or equivalent representation of the circuit which is on the left. So therefore, these I's must be equal. So we can write the left I as we can write it as the source voltage divided by the total resistance. Another thing is that this is source voltage, and because the voltage drop across copper wire is 0, so therefore the voltage drop across the total resistance is also Vs. So therefore, if I apply Ohm's law to R total, I will say that I is equal to Vs divided by R total. All right, so we just applied Ohm's law. Now I want to apply the same Ohm's law to the resistor R1, in which the current I1 is flowing. And we know that the voltage drop across both of them is also Vs because they are connected in parallel. So I1 is the source voltage divided by R1, and I2 is equal to the source voltage divided by R2. So all we did is that we applied Ohm's law 3 times to each current. So each current is transformed from this representation to the representation in which we have resistance value, because we are interested in finding the resistance, so therefore we did this transformation. Now, one obvious thing that we can see is that we have Vs in each term. So if I divide by Vs on both sides, I will get 1 over R total equals to 1 over R1 plus 1 over R2. And now you see that we have an equation that relates R total to the two resistances R1 and R2. Most of the time, we would be interested in finding R total instead of the inverse of R total. You see, here we have inverse of R total. So if I take the reciprocal on both sides, so I can say that R total is actually equal to 1 divided by 1 over R1 plus 1 over R2. Now, this is one way of writing it. If you know the values of R1 and R2, it would be easy to just plug those values in and you will find R total. Another way of writing it is also possible, which I will show over here, is that I will do the following. I will say 1 over R total is equal to, now I will take this first term and multiply and divide by R2. So I will get R2 divided by R1 times R2. And then I will take the second term and multiply by R1, multiply and divide by R1. So I will get R1 divided by R1 times R2. The reason we did that is that we wanted this denominator in both terms to be equal. So now we have the same denominator, so therefore we can say that this equation is 1 over R total is equal to R1, R2, and in the numerator we have R1 plus R2. Now that we have written it in this form, I can now take the reciprocal of both sides, and I will say that R total is equal to R1, R2 divided by R1 plus R2. Now this and this are exactly the same thing. They will give you exactly the same result. As an example, let's see if R1 is equal to 1 kilo and R2 is also 1 kilo. Let's say we have two resistors, both of them 1 kilo ohms. From this equation, I will get R total equals to 1 divided by 1 over 1 kilo plus 1 over 1 kilo, which will be 1 divided by, so 1 divided by 1 kilo is 1 milli. So that will be 1 milli plus 1 milli. Milli is 10 to the minus 3. So I will have 1 over 2 times 10 to the minus 3, which will be equal to 10 to the minus 3. When you take it to the numerator, it will become 10 to the plus 3 and divide by 2, which is equal to 1000 divided by 2, which is equal to 500. So you see our total is 500 ohms. Later on, once you have some practice with this, you will be able to tell that if you put two equal resistors in parallel, the net resistance, or the total resistance, is just half of that. So 500 is half of 1 kilo. 1 kilo is 1000. Now let's look at the second equation and see what we get from there. And we see that our total is equal to 1 kilo times 1 kilo divided by 1 kilo plus 1 kilo, so that's 2 kilo. And in the numerator is 1 times 10 to the 6, and the denominator is 2 times 10 to the 3, which is 1 times 10 to the 3 divided by 2, which is equal to 500 ohms. So again, you see our total is the same as before, 500 ohms in both cases. So both representations just mean the same thing. All right. So that's the case when we have two resistors connected in parallel. Now, the same idea can be extended to any number of resistors. And in this case, let's say we consider a case where we have three resistors and all three of them are connected in parallel, and you can verify that they are connected in parallel because they have the same voltage across them, R1, R2, R3. And you will notice that the voltage is the same across all three, but the current may be different. In some cases, the current may be equal, and that is only possible if the resistances are equal. But if the resistances are different, then the current will be different in all three of them. This is the current I, and I want to represent this circuit using an equivalent circuit where the three resistors are now merged into one resistor, which is called R total. Now in this case, using the same logic as we did before, 1 over R total will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. And you can then say that R total will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that will give you the equivalent resistance of the three resistors connected in parallel. Now let's do a simple example just to get a feeling of this parallel combination. If I have one resistor and another resistor, and I apply 10 volts from here, and I say that this resistor is, let's say, 1 kilo ohm, and this resistor is 2 kilo ohm. So I have two resistors, and they are different values. So I'm going to call this one R1, and I will call this one R2. The current that comes from the supply is I, and the current flows I1 over here and I2 in the second resistor. So this is I2. Okay, so we say that we will first draw an equivalent circuit where we will have a resistor, R total, that will represent both of the resistances, and R total is 1 divided by 1 kilo plus 2 kilo. All right, so that will be 1 milli plus 0.5 milli, correct? So that is 1.5 milli, which is 1000 divided by 1.5, which is equal to 666.6 ohms. So we got our total to be equal to about 666 ohm, let's just say, for the sake of convenience. Now the current that will come from the battery or the source, voltage source, will be equal to, because we will have 10 volts across our total, so we can find the current using Ohm's law. So the current from the source will be equal to the source voltage 10 volts divided by our total, which is 666 ohms, 15 milliampere. So that's the current that will be flowing from the source. Now that we know this current, now let's go back to our circuit and see how much of this current will actually flow through each resistor. So the current through R1, as you can see here, the current through R1 is the supply voltage divided by R1. The reason why it's supply voltage, as we have said it before, is because the voltage across R1 is the same as the voltage of the supply. So therefore I1 is 10 volts divided by R1, which is 1 kilo. So 10 divided by a kilo is 10 milliampere. All right. And R2 is the supply voltage divided by the second resistor R2, which is 2 kilo ohm. And this comes out to be 10 divided by 2, 5 milliampere. And now you can see that the sum of these two currents, 10 plus 5, is equal to 15 milliampere, which is from the supply. So you can see that 15 milliampere comes from here, and then it divides into two pieces. 10 milliampere flows in this resistor, and 5 milliampere flows in the other resistor. And now you can see the smaller resistor has a larger current flowing through it. And it is also, this also makes sense because if a resistor is small in value, then it will offer less resistance to the flow of current, and therefore more current will flow through that resistor. All right, so that's that. So to summarize, I think we can now understand that for a parallel connection, the voltage must be the same. So if I have Vs over here, I will have Vs over here, and I will have Vs over here. So the resistor R1 and R2 are parallel if they have the same voltage across them. This voltage does not need to be the source voltage, but they both need to have the same voltage drop across them. The current through these two resistors will be different depending on their values, and the net resistance, R total, is given as 1 over R1 plus 1 over R2. Now, I want to discuss one more situation here. Let's see if I have a circuit which has this kind of configuration. We have a source voltage, R1, R2, and R3. Now you can see that R1 and R2 are not in series, okay? Because if R1 and R2 are in series, then they should have the same amount of current. The current through R1 is, let's say, I1, here is I2, and here is I3. And you can see that I1 is not equal to I2 because some of I1 actually goes to the third resistor. So we can say that I2 is maybe smaller than I1. So therefore, the current in R1 and R2 is not the same, so they are not in series. Also, R1 and R3 are not in series because they don't have the same amount of current flow. Also, R1 and R2 are not in parallel. So you see, R1 and R2 are not in parallel, not parallel. And the reason is that the voltage drop across them is not the same. Okay, so they are not in parallel. But we see here that R2 and R3 are in parallel, right? R2 and R3 are in parallel. And for future reference, when we want to say that two resistors are parallel, for example, here R2 and R3, we will write it this way. R2 is parallel to R3. Okay, so these two lines, it means that these two are in parallel. So to solve this circuit, what we will do is that we will first find the equivalent resistance for R2 and R3. And when we do that, then the circuit will be modified as follows. I will have R1 as before, but R2 and R3 will be represented by a different equivalent resistance. And instead of writing R equivalent, I'm going to give it a different name so that it's easier to use in future. So I will call it R4, okay? And R1 was over here. So now you see R4 is the parallel combination of R2 and R3. So therefore R4 is equal to 1 over R2 plus 1 over R3. So that is the value of R4. Once we have done, once we have taken care of the two resistors that are in parallel, now this is our new circuit. And here you can see that R1 and R4 are in series. So therefore, the equivalent of these two is another resistor that I will call the total resistance, and that is equal to R1 plus R4. So this way we can just keep on moving from right to left and looking for which resistors are in parallel, which resistors are in series. And once we find the total resistance, then we can find the current coming out of the battery. To demonstrate one example of this situation, I'm going to solve this circuit. I have a resistor over here, and then one over here, one here, maybe another one, and then I have another parallel combination over here, and I guess that's sufficient. So we have R1, R2, R3, R4, R5, R6, and let's say the source voltage is 10 volts. All right. The values of these resistors, we can choose some numbers that are easy to work with. So let's say R1 is 1 ohm, R2 is 2 ohm, and R3 is also 2 ohm. R4 is, let's say, 4 ohm, and 5 is, maybe we can say 4 ohms, and 6 is also 4 ohms. So now we need to see which resistors are in series, which are in parallel. The obvious two that are in parallel are R2 and R3. So I can say that the parallel combination of R2 and R3, I will give it a new name, and that will be R7. So R7 is the parallel combination of R2 and R3. And we can see that this is the parallel of two resistors. Both of them are equal to ohm. And this will be R2 times R3 divided by R2 plus R3. That's the parallel combination. This will be 2 times 2 divided by 2 plus 2, which will be 4 divided by 4, which is 1 ohm. So now you see R7 is 1 ohm, and we could have said that just by looking at the two resistors. If two resistors in parallel have equal value, then their equivalent resistance is just half of that. So that's one, so that is one parallel combination that we solved. The other one is 5 and 6. So let's give it a different name, and that will be R8, which is a parallel combination of R5 and R6, which will be half of 4. You can solve it, and you will see that that will be equal to half of 4 ohm. So therefore, this will be 2 ohm. All right, so my circuit will now have R1, then R7. So the new circuit will look like this: R1, R7, and then we have R4, and then R8. R1, R7, R4, R8. R1, we said we were going to use 1 ohm. So this is 1 ohm, and R7 is also 1, and R4 is 4, and R8 is 2. And this is our intermediate circuit, and in this circuit you can see that all the resistors are now in series. So therefore the total resistance is R total, which is equal to the sum of all of them. So it's 1 plus 1 plus 4 plus 2 which is 8 ohms, and let's say that our source is also 8 ohms instead of 8 volts. So if I say that the source voltage is 8 volts instead of 10, that will make it simpler, and this will give me a current I will be equal to Vs divided by R total, which will be 8 volt divided by 8 ohm, that is 1 ampere. So 1 ampere current will flow from the source. So now this is not 10, this is 8 volts. So therefore we have 1 ampere comes out of the battery. Now that you know 1 ampere comes out of the battery, because this is something that we could not tell before we found our total, right? So once we found our total, then we were able to use Ohm's law on this circuit, and we were able to find how much is the total current. Once we know the total current, 1 ampere, now we know that 1 ampere actually flows in resistor R1. So when 1 ampere flows in this resistor, according to Ohm's law, the voltage drop will be I times R, which will be 1 times 1. So we will have 1 voltage drop over here. So from here to here, there will be a drop of 1 volt. Okay, so therefore at this point I will be left with 7 volts, which is 1 volt less than 8. All right. Now the parallel combination of R2 and R3 is R7, which is also equal to 1 ohm. All right. So therefore R2 and R3 can be represented by R7, which is 1 ohm, and 1 ampere flowing in 1 ohm will cause a voltage drop from this point to this point of 1 volt. All right. So this means that over here, I should be left with 6 volts. Other way of thinking this is that you have this 1 ampere current that is coming from the battery. And when it arrives at this node, it will divide into two pieces. One will go through R2 and the other one will go through R3. Because both of them have same resistance, the current will divide equally. So I will have 1 ampere divided into two pieces, equal pieces. So this will be 0.5 ampere and this will be 0.5 ampere. So half ampere flows here and half ampere flows in R2. And now you can see that when half ampere flows in R2, R2 is 2 ohm, so 0.5 times 2 is 1 volt. So again, there will be a 1 volt drop from the left point to the right point. So therefore the voltage over here will be 6 volts. So this is correct. You can verify it. It satisfies all the applications of Ohm's law in different points of the circuit. Now, so the 2.5 amperes coming in these two branches will come here to this node and they will add up. So when they add up, it will become 1 ampere again. So now we have 1 ampere that is flowing in a 4 ohm resistor. So therefore the voltage drop across this resistor will be 1 times 4, so which is 4 volt. So we will lose 4 volts here, and therefore we will go from 6 to 2 volts. And this means we are going to have 2 volts over here too, and 2 volts over here. All right, now the 1 ampere flows down this way. When it comes to this node, it will divide again into two pieces. One flows through this resistor, one flows through this resistor. And because these two resistors are equal, the 1 ampere will again split equally between the two, and 0.5 ampere will flow in each resistor. 0.5 ampere flowing in a 4 ohm resistor will give me a voltage drop of 2 volts. So from here to here, we will lose 2 volts. And as we have 2 volts over here, therefore at this point we will be left with 0 volts, which is the same as 0 volts because that is our reference, that is our ground. So you see, it satisfies all the requirements. The voltage rise is equal to the voltage drop, the currents everywhere. So it should give you some confidence that the way you did the parallel combination and the series combination, you were able to calculate the total current correctly. All right, so that's it for this video, and I will see you next time. Bye for now.